Very good afternoon to friends in India and Asian countries. Very good morning to the colleagues from and friends from Europe, particularly our speaker from Germany, Prof. Stefan Blügel, who actually does not need any formal introduction. He is so well known in the community, but I'm very happy and thankful to him that from his busy schedule, he managed some time for our webinar series and kindly agreed to give a talk. So again, as a matter of formality, I would just read a few lines about him. So Professor Blügel is a full professor at the Department of Physics of German Excellence University at WTH Aachen. And he is the Institute Director of the Department of Quantum Theory of Materials and a member of the Peter Grunberg Institute and the Institute of Advanced Simulations. He has studied physics at the University of Saarbrücken in Germany, at the College of William and Mary in Virginia in US, and at WTH Aachen University, where he finished his master's degree in physics in 1977, then his PhD in physics in 1988, and his habilitation in physics in 1996. He was a postdoc between 1988 to 1990 with Professor Terakura at the Institute for Solid State Physics at the Tokyo Institute in Tokyo, Japan. The scientific interest of Professor Blügel lies in the field of density functional theory in combination with magnetism, spintronics, spin orbit related phenomena, low dimensional physics, 2D materials, quantum materials. He and his group develops all electron density functional theory methods for these fields. In particular, the full potential linearized augmented plane wave open source code FLIR, and also the Koringa-Kohn Rostocker green function methods. He has tried to develop these methods in the direction of exascale and high throughput computing. He is one of the discoverers of the interfacial Zylowski-Moria interacts. He has advised about 77 PhD students, has published about 520 papers in referred journals, which have cited about more than 22,000 times. He has received several national prizes and a synergy grant of the European Research Council. So just to name a few awards, he got the Theodor Lehn Fellowship from Alexander von Humboldt Foundation in 1988-1999. He also got the Friedrich Wilhelm Prize from WTH Aachen in 1988. In 1993, he got the Heinz Meyer Leibniz Prize from the German Federal Secretary for Research and Technology. In 1994, he got the Academy Award from Academy of Sciences in the state of North Rhine-Westphalia. In 2016, he got the Li Xun Lecture Award from the Institute of Metal Research, Chinese Academy of Science. And in 2019, he got the ERC Synergy Grant 3D Magic for three-dimensional magnetization textures, discovery and control on the maps. So with this brief introduction, I again welcome Professor Blügel to this seminar, and many thanks on behalf of my team, Dr. Brajbhushan Singh, co-convener, and others. And we are really looking forward to a lecture. It's all yours. Just to tell the participants that during the lecture, we don't take questions. If you have any questions, kindly write in the chat box or just say, I have a question. At the end of the lecture, we will take all the questions one by one. So thank you very much. And please start your lecture. Thank you.
Yeah, thank you very much. And thank you very much for this very kind introduction. And I would like to say thank you very much for the invitation. It's a great pleasure to interact with you. And, you know, due to COVID, we have to do it online. I'm a great fan of India, I have to say. I visited India once for a little bit longer. I was in Pune, and from Pune, I traveled to several places. I really enjoyed my time in India. It is a very diverse country in all respects, and I hope when COVID is over to visit the country again if the opportunity becomes possible. Thank you very much for the invitation. I would like to discuss with you. I'm very happy to share with you our research on chiral magnetic skyrmions for Skyrmionics. And I was just very happy a minute ago to see Ashish, because he was with us at a time where this field was developed and he can tell you a lot of stories at the start of this field in our lab. The field itself is probably part of I would say, of a bigger field, which I call Spinorbitronics. And 7-8 weeks ago, you had as an invited speaker, Albert Fert, and he probably gave you a bigger picture and introduction into this field. But the core of this field is actually a very, very tiny interaction, which is the spin-orbit interaction. It's probably a very tiny interaction, which has huge implications. One of the implications is that it is a source of particle-like magnetic textures, these chiral magnetic textures. They are very robust, and they have a very efficient dynamics. So we try to use these as new entities of information-carrying particles. And these are magnetic textures, are topological magnetic textures in a real space. But we have also topological topological textures in momentum space. These are typically the topological materials like topological insulators, but also topological superconductors, which enable dissipation-less edge states, and this dissipation-less edge state can then be used to transport information, but also currents and spin currents across a sample or a device. And a third aspect which I would like to mention is the spin-orbit torques, which enable a very efficient switching of the magnetic textures. And you don't rely anymore on the external B field. This makes it scalable for a device, and has a reduced ohm power to generate the switching. All this together has several aspects of device functionalities, and we would like to incorporate this into this field of spintronics as a subfield of spinorbitonics. Today, I'm basically talking about chiral spin textures. And especially I would like to raise the question, what is actually a magnetic skyrmion? And maybe you're all familiar with ferromagnetism, and this is what you see here in red. So you have at each atom here, you have a classical magnetic spin, say, of a certain size, maybe 2 Bohr magneton, 1.5 or 3 Bohr magneton. And basically in the ferromagnetic state, the spins are aligned at each atom like soldiers in the army. So they are always parallel, and we call that a collinear magnetic state. But what you can immerse on this ferromagnetic state are non-collinear spin textures, basically here shown as 2-dimensional localizations in space. And these localizations in space are stable. So they don't expand, they don't contract, they don't disappear. And probably in India, ice hockey is not very popular, but maybe you've seen it already on TV. So when you have an ice hockey field, you have an ice hockey puck. On this ice hockey puck, they slides basically without friction through the ice hockey field. And this is kind of a vision which we have of a isolated skyrmion. The skyrmion itself is not an arbitrary magnetic structure. Now, the skyrmion, if you zoom into the magnetic texture of a skyrmion, you will see here again the atoms, but you will see that this magnetic texture is of a particular kind. And if you look very carefully, you see that each magnetization direction is exactly taken once in this skyrmion. So if you take this magnetization direction and map it onto a sphere, you see that each point of the magnetization is taken exactly once. You see, for example, at the rim, you match to the ferromagnetic state, which is the North Pole. In the core, you basically have the South Pole, which is here. And then you have the magnetization directions here, for example, in yellow, you point in here, and maybe in blue, you point here. We call this the color coding is according to the XY scale here. We call that a color wheel of the magnetization. And what you see is here you can map the magnetization from the real space into a parameter space on the sphere. And you cover the sphere exactly once. And you know, it is if you cover the sphere exactly once, it means if you want to break this magnetic texture into the ferromagnetic state, you have to rip it off somehow into the ferromagnetic state. And if you think in smooth functions and ripping off a smooth function, this gives you you request an enormous energy to rip off this smooth function. And this is actually what we call the topological protection. So basically, we classify this magnetic texture by some topological number, and this is the topological charge given by the magnetization, which you can find here or here. And the integral of this magnetization gives you basically an integer number. And if this integer number is -1, we talk about a skyrmion. And the interesting property of this topological number is if you apply now a smooth transformation to this magnetization, for example, combing the magnetization or rotating the magnetization, this topological number does not change. So it is something related to your donut. For example, if you think about a donut, you have also a topological number because you have one hole in this donut, but this one hole in this donut does not change. If you make your donut a little bit larger or a little bit smaller, or you tilt this donut a little bit, as long as this hole remains, your topological number of this donut is 1. And here also the topological number of this skyrmion is -1. So we have skyrmions of different types. We have the Niel type skyrmion and the Bloch type skyrmion. And the difference is simply that you have a smooth rotation, that the magnetization of the skyrmion, of the Niel type skyrmion, is in the plane, whereas, for example, varying radially from inside out, whereas for the Bloch type skyrmion, the magnetization points in the direction phi, and moving from inside out. And you see that maybe better here. Here, the Niel type skyrmion, the magnetization is changing along the radial axis, and here you see in the Z plane, whereas here it's changing in the phi plane. And both, since there is a smooth transformation between both have the same topological charge. You have the skyrmions have a certain handedness. That means that depending on a certain quantity, which we discussed a little bit later, which is the Jarodzinski-Moria strength, which can be positive or negative, the magnetization texture winds counterclockwise from inside out, or clockwise from inside out. And these are two-handedness. And you cannot move from one handedness to the other handedness. It's a material intrinsic property. And we have also something which is called skyrmions and antiskermions. The word antiskermion comes from historical reasons. The skyrmion was historically discovered in the field of nuclear physics. It was basically an object in the pion, in the pion field of the nuclear physics, and there you could have the skyrmions represented fermions, and you could have also fermions of the nature of skyrmions and antiskermions. So we translated this word into our field, but I often call this antiskermion also multi-chiral skyrmions. So what is the difference? So if you look at the Niel type skyrmion, the topological charge is, or Bloch type skyrmion, the topological charge is -1, and for the antiskermion, the topological charge is +1. So the topological charges are different, and therefore there is no smooth transformation between the skyrmions to the antiskermions. The topological charge can be thought of as a product of the polarization at the core, which is the same for this, in this particular case of skyrmion and antiskermion. and is the second is the vorticity. This is a one-dimensional winding number. So if you look at, if you wind around the core, you see here, the winding number here is +1. It always, the spin's always pointing to the outside. But here, the winding number here is -1. You see here that if you wind here, you see you have here a twist of the spin pointing from outside to inside to outside to inside. And this change of the vorticity makes it a multi-chiral skyrmion and changes the topological charge from -1 to +1. And actually, now this field has expanded a lot. I discussed so far only axial skyrmions, but there are also non-axial skyrmions. And you see there's a whole zoo and a whole family of skyrmions, of non-axial skyrmions, with very different topological charges, +2 and +3, and different types of +3 and +4. And of course, associated with this is an energy scale. The higher the topological charge, the higher the energy. Most of the skyrmions which I showed you so far, especially the isolated skyrmions, are metastable. So always you are, the ferromagnetic state is frequently the ground state, not always, but frequently the ground state. And what happens is, if you look at this skyrmion, you can go to the ferromagnetic state, but this means you have to change the topological charge. And changing the topological charge is related basically to the existence of an energy barrier, which I show here. And so that means in order to pass the to change the topological charge, you have to overcome a certain barrier, and this barrier means that you have a certain protection, and this barrier is then related to a certain lifetime of the skyrmion. And depending on this barrier here and the prefactor, which also changes a lot when you move from the skyrmion to the ferromagnetic state over the barrier, then the lifetime can change depending on the material, from nanoseconds or picoseconds to the lifetime of the universe. Now let me comment one word on the materials realization. These skyrmions are not only theoretical fantasies of theoreticians and mathematicians, but it's also realized experimentally. For example, there are two basic classes of stabilization mechanisms. One are the interface stabilized germions. So you have, for example, here a substrate. Typically, you have substrate with large heavy metal substrates, like substrates with large spin orbit interactions. You will see that for a second why this is the case. Then, for example, you have here typically a ferromagnetic film like iron. And then maybe you have some other films here, for example, palladium, to optimize a little bit the exchange interaction. Or you can have multi-layers of cobalt, iridium, platinum, and others. And these are, due to the interface, you break the inversion symmetry. You have spin orbit interaction. And this leads basically to this Jarodzinski-Moriya interaction, to which I will come in a second. And this enforces the formation of skyrmions. And you see here an experimental study from the Wiesendanger group using spin polarized scanning tunneling microscopy. Here are schematic sketches, and here are the experimental results. So basically, without magnetic field, this B field is 0. You have here a magnetic structure, which is a stripe structure. This stripe structure you see here. So it's so you have here a magnetic spiral, which spirals along this direction, with magnetization pointing up, magnetization pointing down. You apply here a magnetic field, and depending on the size of the magnetic field, you see slowly the emergence of this skyrmion phase. If you increase the magnetic field a little bit, you have more skyrmions. And if you increase the magnetic field very much, the skyrmions have basically collapsed, and you are basically back to the ferromagnetic state. And this you see here basically as a sketch. But you have not, so yeah, and with this you can measure out the Skyrmion radius. You see here the Skyrmion radius as function of the magnetic field. And you see in this system that the Skyrmion radius is very small. It's typically of the order of 1 to 3 nanometers. And what I also like to point out that the Skyrmion radius can depend very much on the orientation or the crystal structure. Here, for example, the palladium is grown HCP relative to iron and cobalt, iron and iridium, and here it is grown FCC, and the stacking difference leads already to a large difference in the Skyrmion radius. But there are also bulk materials stabilizing Skyrmions. For example, typical materials are the B20 alloys. These are B20 structures. So do you have examples of, for example, famous examples in iron germanium, manganese silicon, manganese germanium. So here you have structures which have broken inversion symmetry. And actually the crystal structure has already some chirality. You can have right rotated structures and left rotated structures. And due to the structural formation, the structural rotation is imprinted in the magnetic structure, and you can have then right rotating and left rotating magnetic structures. And you see here for manganese silicon, historic example where the Skyrmions in the bulk phase was found for the first time. This is a phase diagram of the magnetization versus the temperature. You see without magnetic field, you come from the paramagnetic limit, you have a phase transition to the helical state. And if you increase the B field, you go from the helical state to the conical state. And there is one pocket, and this is called the A phase typically, where you can find the formation of the Skyrmions. And you see here a Lorentz microscopy image from the Tokura group. And you see here the XY magnetization of the Skyrmions in the Skyrmion lattice here. So you can find single Skyrmions, but you can also form Skyrmion lattices. And here in this pocket, you form the Skyrmion lattice. And you can also take bulk crystals, but you can also take this material and form out of the bulk material thin films, which are thicker, much thicker than these films. But the outcome is slightly different because here in the thin film regime, you have a substrate, and the substrate introduces some strain, and the strain changes the magnetic anisotropy, and therefore this A phase may change very much in size due to these additional strains. So you can maybe extend this A field if you grow it as thin films. And if you grow it as thin films, you have to be careful that you grow only single phase. Otherwise, you have in some parts of your sample, you have the A phase, which leads to right rotating magnetic structures, and in the other phase, in the other area of the sample, the left magnetic structures. And then, of course, the Skyrmion cannot move freely in these magnetic structures. So let me say a word on the Skyrmions for applications. Obviously, the Skyrmions exist. The Skyrmions are small. The Skyrmions are stable. And therefore, it is a possibility for new, as a new nano-sized particle for this disruptive change of the information technology. It has a nanoscale size. This promises high data densities. Skyrmions are homochiral. It has only one chiral sense. It is topologically protected. It offers thermal stability. The Skyrmion can be displaced by currents in fast motion. So it cannot only move in one direction, it can move in two directions. This gives you new opportunities for data flow. Depending on the current, it can reach fast motion with high data flows. And due to the non-complanar texture, it allows electrical detection, not necessarily magnetic detection. And the first vision of this Skyrmion was an application in terms of a solid state memory, where Skyrmions are present ones and the absence of Skyrmion 0 for a new type of memory, new type of race stack memory. So it's fit for the field of spintronics. It allows injection of Skyrmions, the transport of Skyrmions, the detection of Skyrmions, the manipulation by reasonable fields and currents. But if you put Skyrmions in a technology, there are of course criteria in order to compete with other competing technologies. So the Skyrmions should be, the films should be thin, but not too thin, so that you can sputter it properly. So maybe 3 layers. You should find small Skyrmions, but not too small. So maybe 10 nanometer Skyrmions are good. They should be stable above room temperature and small magnetic fields. And maybe they should realize 1,000 kilometers per second. And maybe one future of this Skyrmion is actually, you know, for reservoir computing and deep learning. This might be a second opportunity, or a different, completely different opportunity for Skyrmions in the field of neuromorphic computing. So now let me come to the point of simulating and describing Skyrmions. Certainly, I would say if you have a spin texture, a very natural description of a spin texture is maybe an atomistic spin lattice. So you have here the Heisenberg exchange, you have the Jarodzinski-Moriya interaction, to which I come in a minute. We have the magnetic anisotropy, and we have the dipolar fields. And if you have these parameters, the Heisenberg exchange, Jarodzinski-Moriya interaction, and so on, you can put this into a Langevin equation. You can do Monte Carlo studies to do the thermodynamics. So you can do a lot of atomistic simulations. And this, we have developed atomistic simulation code, Spirit, which is free to use, which you can even run on your mobile phone. And with this, you can basically play a little bit. You get a feeling for the dynamics, for the stability, for the lifetime, for the motion with external magnetic and internal fields of a spin texture. It was originally invented for high school students, because every high school student nowadays in Germany has a mobile phone, so they can play in the lectures. But then the experimentalists liked it so much, so that we moved it, put it forward in this direction. It's a quite nice tool. And then, of course, a second level of describing the Skyrmions is the micromagnetic model. The advantage of the micromagnetic model is that you have work with continuous field. You can all use your analysis tools, which you have developed in the mankind has developed over the last 250 years, and can do analytical conjectures. And this is, of course, very, very helpful. And of course, there is a relation between the Heisenberg exchange parameter and the spin stiffness, and the microscopic Jarodzinski-Moriya interaction, and the spiralization, and the micromagnetic magnetic anisotropy, and the macroscopic magnetic anisotropy. And the relation is basically given to you by the long wavelength expansion of the magnetization at the magnetic moment at point I, expanding it into kind of a texture by expanding the magnetization at point J at the magnetization at point I, and using basically a Taylor expansion. And then you see that the spin stiffness is basically related to the Heisenberg exchange, and the spiralization is related to the micromagnetic Jarodzinski-Moriya interaction. And then there is a third level of theory, which is basically our core business. This is the DFT model, where we try to understand these parameters J, D, the magnetic moment, magnetic anisotropy, directly from a density functional theory, using a total energy calculation. And from these total energy calculations, you can, for example, obtain these parameters A, D, and K directly by winding the magnetic structure and calculating the total energy difference of this winding magnetic structure, which we express in terms of a wave vector of a spin spiral state. The second derivative gives you basically this spin stiffness. The first derivative, the Dzierżynski-Mourier interaction. The other possibility is that you do infinitesimal rotations, and these infinitesimal rotations, you can basically, with these infinitesimal rotations, you can basically get these Heisenberg exchange parameters and the Dzierżynski-Mourier interactions. And this we have implemented in different codes. The Fleur codes is best for these micromagnetic model parameters. The KKR code is best for these infinitesimal rotation and microscopic parameters. Now let me come to this energy functional, and I come back to this energy functional in the micromagnetic description with the spin stiffness, the magnetic anisotropy, and the magnetic field. And what I'm looking now is, I'm taking now this skyrmion, I put it into my ferromagnetic background, and I'm asking myself, how does this energy functional react if I put this skyrmion in and basically, stretch the skyrmion a little bit? Is the skyrmion stable or non-stable? Is the energy increases or doesn't increase? And by this, simply what I'm doing, I'm taking the magnetization of this skyrmion and stretch the magnetization a little bit by this basically by this linear scaling. And what you see in this, and then of course the energy depends on this linear scaling parameter. And what you see, you get here a square behavior due to the differential here. And since you have here the first derivative square, you get here also a 1 over lambda square behavior. When if you multiply all this, you see that the energy functional has a quadratic behavior as function of this lambda. And the minimum of this quadratic behavior is exactly at lambda equals 0. So what it means in 2 dimensions, the Heisenberg exchange is scale invariant, and your magnetic anisotropy or the magnetic field basically squeezes the skyrmion to death, and therefore you cannot have a skyrmion in 2 dimensions in this energy functional. This changes, in 1 dimension, this is not a problem. In 1 dimension here, for 1-dimensional magnetic structures, here you have only a linear differential. You have here a lambda, and your energy functional looks like this. And this energy function has a minimum, and you know exactly what this minimum is. This is basically exactly your domain wall. So if you have a ferromagnetic state here, and you have a ferromagnetic state here, and they point in different directions, say in positive Z and in minus Z direction, you can have here a localized domain wall, and this localized domain wall is stable with a length given by the exchange divided by the magnetic anisotropy. And in 2 dimensions, this is not possible. But it is possible if we add to this energy functional this Dzierżynski-Mourier interaction, which has in this function, in this micromagnetic energy functional, this form. It has a linear gradient here, and it basically causes a chiral symmetry breaking, because left rotating and right rotating is energetically different. And the necessary condition for this Dzierżynski-Mourier interaction is the spin-orbit interaction and is the broken inversion symmetry. And this combination is necessary to get this Dzierżynski-Mourier interaction. And therefore, we have seen that the materials we discussed are materials which have broken inversion symmetry, for example, due to the interface or in the bulk, and have typically a large spin-orbit interaction. And therefore, we involve typically heavy materials. And so now if you include now the stretching transformation, you see we have here an additional, due to this, an additional 1 over lambda, which gives you together with this lambda square a linear form. You have here a local minima, which is not at 0, but at finite lambda. And this tells you that you to do this linear chiral symmetry breaking, you get basically a stabilization of 2-dimensional objects, which is this axial symmetric skyrmion. So this micromagnetic energy functional has basically a contribution which is given by this chiral tensor here, which is this term here, and the spiralization tensor here. And the spiralization tensor has, for example, for cubic symmetries is extremely trivial. It's a unit matrix with one parameter, which is this spiralization. For a certain interface, like the interface we discussed for iron on iridium or cobalt on platinum, it has this form here. And due to this form here, I should say this has a one scalar degree of freedom, and this one scalar degree of freedom defines the size of the skyrmion and the rotational sense of the skyrmion. It depends on the material, and it basically depends on the electronic structure of the material. And then you have basically a matrix which defines the symmetry of the skyrmion. The upper one gives you a Bloch skyrmion, and the lower one gives you a nail skyrmion. And we call that a rank 3 bulk DMI with one scalar degree of freedom. And this we call a rank 2 film DMI, also of one scalar degree of freedom. And you can have now different symmetries here. For example, here a bulk D2D symmetry. And if you have this bulk D2D symmetry, you see your matrix has here one inversion. And this means automatically that your skyrmion, you cannot have skyrmions in such a symmetry. You must have an antiskyrmion. So you see here the antiskyrmion versus skyrmion. The antiskyrmion is determined by the crystal symmetry of your bulk material. And what we found out is the determinant of this matrix determines, the sign of the determinant determines whether this is a bulk skyrmion or an antiskyrmion. So to look at the reality check, so we had discussed already the Bloch skyrmion for bulk systems. We have already discussed the nail type skyrmions in film systems. We found recently also, not we found, the group of Stuart Parkin found Antiskermions for particular Heusler alloys with 2D D2D symmetry. And the question is whether we find that we have also the possibility of antiskermions in film systems. And this has not been found yet. But we conjecture their existence. So far, all kinds of symmetries have been studied. The isotropic rank 3 bulk DMIs, for example. We know that certain crystal structures form skyrmions, other crystal structures form antiskermions. We have the rank 2 DMIs for all symmetries larger than CN3. We have exactly for all these, we have only isotropic DMI. Isotropic DMI means we have only one parameter controlling the Jalatinski-Moria interaction, either right rotating, left rotating. Either you can have skyrmions or you can have antiskyrmions. But we have also certain symmetries which are not dictating the symmetry of the underlying skyrmions. And these are, for example, symmetries which have C2V symmetry in the film system or lower than 2dV, C2V. And these we call the anisotropic rank 2D DMI. And here you have not one independent parameters, but you have two independent parameters. It is simply determined by the electronic structure, how large, or by the strain, how large these parameters are. So, and if the determinant is of this determinant is smaller than one, then you can have a skyrmion and an antiskyrmion, but the antiskyrmion has a lower energy. If the is positive, you can have skyrmions and antiskyrmions, but here the skyrmion has the lower energy. But if these two energies are the same, then you have what we call a rank 1 DMI, anisotropic DMI, and then the skyrmion and antiskyrmion are energetically degenerate. And in this particular case, you could have a racetrack memory where you have skyrmions and antiskermions, skyrmions and antiskermions simultaneously. One is representing the 0, one is representing the 1, and you can also build logic devices out of this. So far, we have not found the right material which has this property. And of course, we want to have sub 10 nanometer skyrmions at room temperature. So I've talked about these skyrmion, sub 10 nanometer skyrmions. So I should also discuss at least the skyrmion radius. So let's have a look at the skyrmion radius. I consider my energy functional. I consider axially symmetric skyrmions. For the time being, I don't discuss the demagnetization field. And since I have axial symmetric skyrmions, I can make an ansatz for axial symmetric magnetization densities. And I use basically here a polar coordinate system to make my life easier. It's typically a nail-type skyrmions, which varies along the radius in the Z-plane. And then what I'm doing is I'm minimizing this energy functional in order to find this optimal skyrmion profile. And this optimum skyrmion profile is basically given by this profile as function of the radius. And this leads to the skyrmion profile equation. And if you look at this equation is highly nonlinear. It depends on the sign. It depends on the sign square. So it's a highly nonlinear equation. And I can solve this equation numerically by certain boundary conditions. I want that my skyrmion in the center, the magnetization of the skyrmion in the center points down, and infinity it points up. It attaches to the ferromagnetic state. And I have written this equation in a certain form so that only one parameter here is left. This is a dimensionless parameter kappa, in which the spin stiffness, the magnetic anisotropy, and the Jarodzinski-Moria interaction enters as a dimensionless parameter. And the radius rho is basically scaled with respect to the domain wall width. Then I basically can solve it, and I can define what is a skyrmion radius. And the community has decided that the skyrmion radius is the radius where the magnetization in the Z direction is 0. So it's basically somewhere here. And basically the skyrmion radius is given in the units of the domain wall width. And I leave out to make my life easier, I leave out the magnetic field, I put it to 0. And then I solve this equation, and here you see the radius of the skyrmion as function of this parameter kappa. And if you look at this graph, maybe you see nothing. And that is correct. You have to zoom in a lot. You see this radius is a highly nonlinear function of this parameter kappa, which depends on materials parameters. And you have to zoom in really a lot to see that this skyrmion radius is changing highly nonlinear with this parameter kappa. And that means, as an experimentalist, if you have small variations, depending in which regime you are, it can happen that in small variation of your growth parameters, you can vary the skyrmion radius a lot. And I don't go into the analytic expressions. Let's look at the few limits of this equation. So if I say the exchange is the most important part, and the DMI and the anisotropy and the Zeeman field is unimportant, then my equation becomes much simpler. And the solution of this equation is known as the Belaviev-Polyakov solution. And which I have shown here, you see the skyrmion first has a strong core in which the magnetization changes very rapidly, but it has a huge tail in which you still feel the skyrmion, and the skyrmion radius is relatively small, but the tail is relatively long. That means, in other words, you have still a large repulsion to other skyrmions. So this is the Skyrmion Polyakov solution. And then there is another limit when you say that, okay, I studied the limit of large distances, of large radii, then I can take this out, and then you come to the domain wall solution. And this domain wall solution, you know, from one-dimensional domain walls, so you have a situation where the magnetization doesn't change for long, then you have a rapid change of the magnetization, and then it doesn't change for long. So these are the two limits, and we have basically developed a Skyrmion radius calculator, which calculates you the radius of the Skyrmions in fractions of a second if you put in the right numerical parameters, and then basically you push a button, and then your Skyrmion radius is calculated for you. This is very handy for experimentalists. And now I would like to come to the Skyrmions, to my last point, to Skyrmions in magnetic multilayers. The magnetic multilayer is an extremely versatile magnetic system, because you can choose the thickness, the layer composition, the growth conditions. You can choose between the ferromagnetic and between a ferromagnetic, and you can choose the coupling between the ferromagnetic layers to be ferromagnetic or antiferromagnetic. You can vary, so to say, the interaction between those through different metals. You can modify the Jarzynski-Moriya interaction by sliding in here heavy spacer materials. So it's basically an infinite system with which you can tune all kind of properties. You can you can produce materials with a very strong out-of-plane magnetization. You can vary the exchange bias fields. This is basically, you can do infinite systems with this system. And probably you can tune this system also to find the right Skyrmion for your application. I would like to point out that if you calculate the Skyrmion radius as, for example, as number of these, say, cobalt layers. I should say the most popular system here is cobalt platinum. By far, the most investigated system is cobalt platinum. It is the system which has the closest relation to technology, and there's a lot of experience in this field on this system. And therefore, we looked also at, for example, cobalt platinum. And what you see is, as I mentioned, the cobalt radius, the Skyrmion radius can vary very, very much by very little, by changing the cobalt thickness very little. But if you include also the full demagnetization into the radius calculation, then you see the rate due to the demagnetization field, the radius becomes faster large, and this you don't want. You want to have a small Skyrmion radii. So the demagnetization field increases the size of the Skyrmion, and therefore we typically want to work with, instead of ferromagnetic coupled Skyrmions, we want to work with antiferromagnetic coupled Skyrmions, such that the demagnetization field cancels in first order. And then what we also noticed is, if you look at the experimental work, you have in reality very complicated stacks. So you have tantalum, platinum 8, cobalt 1.47, ruthenium 0.75, blah, 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 nanometers. So if you translate this into atomic layers, you have here 35 platinum layers, 7 cobalt layers, 3 to 4 ruthenium layers, 3 platinum layers, and so on. So in total, you have maybe, even if you make approximations, if you say 35 platinum layers, if you want to model this as a realistic stack, you replace this by 5 layers and you replace this by 5 layers, you have 34 different layers. And you have 14 different magnetic layers. And I've shown you before that depending on the stacking, you can have very different magnetic radii due to the very different Jarzynski-Moriya interaction. So you have easily 2 to the 34 possible stackings. And this makes it to 4 billion different systems. Even if you do high throughput computing, this is too much. So we simply need approximations if you want to simulate these things. So approximations are needed, and we investigate, basically periodic systems. And we have simplified stackings and compositions. So we work with cobalt N, platinum M, ruthenium L, and this we repeat infinite time. And then we can have different stacking orders. So we can have FCC or HCP and so on. And what I show you in this talk is only one particular example, which is N equal M equal L equal 1. So basically, I go with you through DFT results of Z, cobalt, platinum, 3 layers, each of them 1 layer thick in the 1-1-1 stacking, and then varying Z. And I'm varying Z along the 4D transition metals, yttrium, zirconium, niobium, molybdenum, up to cadmium, include copper, zinc, and gold. And what you see is basically, if these elements here are gray, then they couple antiferromagnetically. And if you see they are pink, they couple ferromagnetically. And this you see basically here. Here you see the energetics of the different systems, of the different stacking between the cobalt layers. With the cobalt layers here in blue, you can have ferromagnetic stacking, you can have antiferromagnetic stacking. You see here the energetics, and everything which is gray has basically an antiferromagnetic stacking, and everything which is pink has here a ferromagnetic stacking. These are the typical energies involved. And then you see the magnetic moments of cobalt varies depending on the neighboring element, whether you have yttrium or ruthenium or silver. Basically, you have a change of the cobalt moment, and the change of the cobalt moment translates somehow to the stiffness of the yes. I will finish very, very soon. And with this, we changed the magnetic stiffness. And with the change of the magnetic stiffness, we also changed the Curie temperature of the system. In addition, we calculated the magnetic anisotropy, and we see that certain systems are out of plane, certain systems are in plane. For Skyrmions, we need out of plane magnetization. So these are very good systems for Skyrmions. And then we also looked at the Jarodzinski-Moria interaction. You see, we cross here a sign. So some of them are left rotating, some of them are right rotating. Here you have a strong magnetization, a strong Jarodzinski-Moria interaction. And now we put all this together, and you see indeed that the Skyrmion radius here, depending on the system, you can vary the Skyrmion radius here by according to this rapid change, and the Skyrmion radius varies here by several by a factor 5 or factor 50 even in the units of this domain wall width. And the units of the domain wall width is about 4 nanometers for this type of systems. And this gives you, this is the domain wall profile. So it's a kind of Belavin-Polyakov type of profile. And this is all consistent with experimental studies. So we have here typically domain Skyrmion radius of 3 nanometers. So I think, and now I would like to stop. And I would like basically to thank you for the attention. Otherwise, my talk will be slightly too long.
Stefan, actually, if you like, you can finish those 2 slides comfortably. We have no problem. I think somebody raised their hand, and maybe you thought I have not stopped you.
Okay, so, sorry. Okay, sorry, I got nervous. Yeah.
No. I think somebody just raised their hand, and you probably got a ping. So
yeah, I thought maybe you raised the hand and said too slow. Yeah, sorry. I would like to say that this was done basically for a little bit academic stackings, which you can realize, for example, in an academic environment, like in an STM experiment, you can exactly produce these tri-layers of, for example, zirconium, cobalt, platinum, zinc, cobalt, platinum. But maybe you also want to know what happens for bigger systems. And this basically, we are extrapolating now our results from this limit of 111 to a thicker cobalt. What happens if we introduce thicker cobalt? And if we introduce a thicker cobalt, we know that the magnetic anisotropy and the Jarodzinski-Moria interaction are basically interface properties. So if you have more layers, basically the magnetic anisotropy and the Jarodzinski-Moria interaction does not change very much. So the scaling is basically 1 over thickness. This is different for the shape anisotropy. The shape anisotropy is increasing with the number of cobalt layers. So per cobalt layer, it is the same. And also the spin stiffness is increasing per cobalt layer. So in general, it remains the same if you scale it per cobalt layer. So if you take this into account, you see that your famous kappa parameter, which determines the position of the universal curve of radius versus kappa, is now changing. First, it increases due to the spin stiffness proportional to the cobalt thickness, but due to the shape anisotropy, it decreases quadratically. That means you first increase your kappa with the thickness, but you come back due to the shape anisotropy. And maybe some of you remember that the shape anisotropy, if you increase the shape anisotropy, the shape anisotropy tries to align the magnetization to in-plane. So at a certain thickness, you have a reorientation transition from out of plane to in-plane from a certain thickness of the number of cobalt layers. So prior to this, you are somewhere here, and then you see that suddenly your skyrmion becomes very large and maybe unstable. And as you see that the skyrmion radius depends now on the number of layers. And this we have put into a context now. You see, as function of the cobalt layers, you see that this crazy, very tiny Stremian radiuses, which are totally artificial, now becomes relatively large, and you can go into a direction of these 10 nanometers. So these are the ideal Skyrmions, the 10 nanometer Skyrmions, and you can control that with the Skyrmion thickness. So for example, for copper or for rhodium system or for the zirconium system, depending where you want to have your Skyrmion radius and the growth of your samples, you can reach this 10 nanometer limit for different systems. And with this, I think I want to stop and thank you very much for your attention and for your patience.
Okay, thank you so much, Stefan, for this wonderful overview and exciting new results in a way, unpublished results. So really, we enjoyed, and I'm sure all the participants must have enjoyed as well. So before we take some questions, I got some message that people want to have your recordings because they join later or something. So I think I have your permission to put in the YouTube, yeah? Okay.
Yeah, sure.
All right. So before I take some questions from other, I have actually one curiosity. If you go to in the beginning of your slides, somewhere around 12, 13, you showed like a potential well, double potential well. Yeah, that one, 13. So these two ground states, or one ground state, one metastable ground state. I believe the metastable ground states are for the Skyrmions, and the ground state you refer to like complete ferromagnetism. That's what you were saying? Okay.
Yes. So in the simplest case is a ferromagnetic ground state, but it could be also a helical state. For example, for the B20, it's probably a helical state, which is the ground state.
Okay.
So for the thin films, it's a ferromagnetic state, but for B20 materials, it's the helical state. And what this graph shows, I did not say very well, is the barrier here is different. It can be large, it can be small. And the difference is the profile. Depending on the Skyrmion profile, you can have high barriers and low barriers. So, for example, if you have this Belavin-Polyakov type Skyrmion, which is the Skyrmion where the DMI is very small compared to the exchange, then the barrier is very, very small. But if you have these domain wall type Skyrmions, then the barrier is very high. But if you have the domain wall type Skyrmions, then you might be in a regime where you have to be very careful what you want to do. Because then you are in a regime where maybe this radius changes very quickly with materials parameters. So it depends very much what you want from this Skyrmion. If you want, for example, a Skyrmion which, who doesn't scale very much, then maybe you're better in this regime. But if you're in a regime maybe where you have very stable Skyrmion, it might be you have to change your material parameters a little bit.
All right, thank you so much. I mean, if the barrier height is, maybe we can, yeah. So if the barrier height is small enough, then in principle, the thermal energy can actually make the imbalance. Yeah, so it can be a problem, isn't it? So
yeah, if the barrier is not high enough and your temperature is too high, then the Skyrmion will disappear.
Yeah. So is there like a way that we can design how to make the barrier height large enough?
Yeah. So the barrier height here is controlled by your micromagnetic parameters. So if you make the Dzhalodzinsky-Moria interaction, wait a second, I have to think. If the Dzhalodzinsky-Moria interaction is probably strong enough, your barrier is higher. So basically, this barrier height is controlled by your micromagnetic parameters, whether you have a certain spin stiffness, a Dzhalodzinsky-Moria interaction, and so on. And what you need is a strong DMI to get a larger barrier.
And I think also the anisotropy helps in making the barrier higher, isn't it?
Yes, that is true. Wait a second, I have to think. Yeah, I have to think a little bit what makes the barrier optimally high. Basically, if you are in the, you see that here, if you are in this regime, the barrier is high.
Okay.
And this regime is a regime where, so to say, the domain wall is relatively small. And if the domain wall is small, then you are basically in the regime where your magnetic anisotropy is large.
Yeah.
Yeah.
Okay. Thank you. There are actually a few other questions by others. I just have one more question regarding this kappa. What is actually, it's like a parameter defining the anisotropy. I'm sorry, the anisotropy, the DMI plus the exchange constant. And for different materials, the exchange is not so different. So it's basically a computation between the anisotropy to the DMI.
The exchange changes also. Say, for example, also, here you see, wait a second, I find this transparency quickly enough. So you see here, here we have the exchange. Wait a second, here. See, here's the exchange. Okay. So the exchange can also vary a lot. So okay, here, for example, for ruthenium, for rhodium, the exchange is large. But for example, here for those materials, the exchange is relatively small.
Okay, so what is the
this has also implications on the Curie temperature.
So if the exchange is high, then the Skyrmion size like small, how is it?
If the exchange is small, then the Skyrmion size is small.
Okay. All right.
Yes.
Okay.
Because what happens if the exchange is small, your kappa is small.
Yeah.
And the kappa, if the kappa is small, the radius is small.
Okay. It sounds good. Thank you so much. So then I will take some questions by others. Professor Priya Mahadevan has a question. Priya, please go ahead. Priya, please unmute and ask your question.
Sorry.
Please.
Stefan, hi. I had a small question, a naive question. In one of your view graphs, you had, you were changing the atom, and in some of them, they were, you had plane, you had the moments in plane, whereas in some of them, you had the moments out of plane. So it's not, as far as I understand, it's not just shape anisotropy, but something else also which determines whether you have perpendicular magnetic anisotropy or in plane, right?
Yeah, sorry. And this graph, which you mentioned, which is probably this one, I did not include the shape anisotropy at all. So basically what you hear is, this is basically the spin orbit contribution.
So it's so
basically what we calculate here is simply the total energy out of plane versus the total energy in plane.
Okay.
And look at, and switching on the spin orbit interaction. And this gives you this energy difference.
Okay, so I mean, so then it boils down to a, so would you have in-plane anisotropy? I mean,
yes, then then you have basically what happens is molybdenum, niobium, and technetium. Of course, technetium is experimentally not very important, but niobium and molybdenum have obviously an electronic structure, so such that the cobalt magnetization turns in plane.
I see. Okay.
So basically, what I'm showing here is the easy axis of cobalt in this tri-layer of platinum, cobalt, for example, molybdenum or niobium. But cobalt, as a neighbor of molybdenum, it is interacting with the electronic structure of molybdenum, is interacting with the electronic structure of niobium, such that the orbital moment or the spin moment of cobalt is pointing in the plane.
I see. So does this depend then on which orbitals are interacting?
Yes.
Or crystal field effect? Or?
Yes.
Okay.
Yes. Yes.
Okay. Thank you.
It's basically the D character of molybdenum and niobium. So to say, if you want to think about orbital representations, which is responsible, you can maybe attach to these particular bands L or an M quantum number, which is maybe ±2, and then it's basically probably it's actually M ±1, and then it's probably pointing in plane.
Okay. Sure. Thanks.
Whereas here, you probably go to M equal 2, and then it's out of plane.
I see. Okay.
Okay, thanks, Priya. Ashish, please unmute and ask your question.
Hi, Stefan.
Hi.
I have one question that all these things. So, what about this light atom thing? That suppose is it possible that one can engineer light atom and then get a Skyrmion as like in heavy metal things? I need your opinion on that thing.
You can also have nowadays people do low temperature work, maybe also graphene becomes, under certain conditions, magnetic. And maybe under these conditions, maybe also graphene can hold skyrmions. But might be a low temperature effect. The skyrmions might be very huge. And maybe the spin orbit interaction comes partly from the substrate of graphene, which is maybe has some hybridization. So I would intuitively think maybe it is possible, but it's probably very fragile and is probably not the main concern of my personal work.
Okay.
But somehow, if you want to stabilize the skyrmion by the Dzyalzinski-Moriya interaction, you need to some extent some spin orbit interaction. But the spin orbit interaction not necessarily must come from the d electrons. It can be also coming from p electrons. So it could be also bismuth telluride, which is a substrate, which produces a significant amount of spin orbit interaction. Or it can be even germanium, which is sufficient. But it's probably, of course, you can have also oxygen and nitrogen involved, but we would, I would say, producing a large gradient. So you need, so for this Dzyalzinski-Moriya interaction, you need the symmetry breaking. You need symmetry breaking and spin orbit interaction. But what is actually symmetry breaking? More specifically, you need a symmetry breaking of the wave function. And a symmetry breaking of the wave function you can induce if you have, for example, a large charge transfer to neighboring elements. If you have a large charge transfer to neighboring element, you have in some language spoken a large crystal field in a certain direction. If you can create this large crystal field, then you can also multiply your Dzyalzinski-Moriya interaction, even if you have a smaller spin orbit interaction.
Okay,
so you introduce, for example, charge transfer, asymmetric potentials, asymmetric wave functions on the cost of less spin orbit interaction.
Oh, you mean that this Dzyalzinski-Moriya interaction can be tuned with your charge transfer energy and
Yes.
the effective spin orbit coupling.
Yes.
But that has the spin orbit coupling is a less small role compared to the charge transfer energy then. But
yes,
you mean
you can,
spin orbit coupling at the end. It's ultimately
yeah, you can outbalance both. Yes.
No, with the balancing. Okay.
Yeah.
Okay, thanks, Ashish. So I take some questions from the chat box. So Smriti asks two questions. I think we have already discussed one of them. What does the kappa physically signify? And the second one is, can skyrmion be non-circular?
Yes, the skyrmions can also be non-circular, that's for sure, because you can have strain fields, which are uniaxial in the substrate. And this strain field changes the magnetic anisotropy and also the Dzyalzinski-Moriya interaction. So I assume that the Dzyalzinski-Moriya interaction is homogeneous in all directions. And if you have a strain field, this might be different. And then you can have, for example, also elliptical skyrmions. And in a very special case, you can also have so the skyrmions I discussed were axial symmetric skyrmions. A modification of these axial symmetric skyrmions are basically elliptical skyrmions. But in reality, of course, you can have more complex skyrmions, the ones which I have shown. You can have a total zoo of skyrmions if you allow non-axial textures.
Yes.
There was one question about copper. You mentioned copper.
Yes, he said, I think she meant, what is the significance of the kappa?
Kappa is, we studied several elements, of course, 14 different. One of them is kappa, and kappa and silver have the advantage, basically metals where basically the d electron is very deep. So basically interaction to d electrons is very small. And basically you have only s and p electrons at the Fermi energy. So therefore we tried copper, gold, where the the d electrons are not involved, in opposite to palladium, rhodium, or ruthenium, where the d electrons are the d electrons are moving through the Fermi energy. And you can see that for copper and silver and gold, so to say, the d electrons play a minor role in the Dzhalinsky-Fourier interaction and the magnetic anisotropy.
Yeah, thank you. So there is a question, out of curiosity question. Can you tell how you perform micromagnetic simulations?
The micromagnetic simulations usually there are very good packages. Also, I myself use the micromagnetism basically for analytic studies. The micromagnetic studies for basically studying certain approximations and regimes and stability regimes. But if you want to do a micromagnetic calculation, there's quite a number of open source codes available, the UMF code maybe and other codes, with which you can do rather systematically micromagnetic simulations. If you need suggestions for a particular code, the person should send me an email, and maybe I can send him a particular code. I myself, I don't have a particular code, but we use several.
Yes, I mean there are many MUMAG, NMAG,
Yeah.
So yes, so I think by this one, if you have further questions, you can contact Professor Blügel directly. Next question by Satya Prakash Pati. He's asking if two skyrmions of same radius annihilate, what would be the resultant radius?
Two skyrmions
of similar or same radius annihilate.
Usually, I would say that two identical skyrmions, when they approach each other, they have a repulsive force.
Yes.
So basically, they try to escape each other. If a skyrmion and an antiskirmion comes, then it depends on the orientation of the antiskirmion. So if the antiskirmion is oriented in a way that the rotations are the same, then they're also repulsive. But what happens to this antiskirmion, most likely it might rotate. It depends on the situation. It might rotate, and then it will attract the skirmion, and then it will annihilate, and then spin waves will emerge.
Yes, thank you. Next question by Sumit. Is it possible to form skyrmions in triangular antiferromagnets without DM interactions?
Yes, this is also possible. These are not the chiral. So we distinguish with different types of skyrmions. I discussed here chiral skyrmions. The chiral skyrmions are basically derived from this Dzhalinsky-Fourier interaction. But I did not talk about this. Wait a second, please. For example, if I take this functional form here, so I cannot have skyrmions here because I have no Dzhalinsky-Fourier interaction in 2 dimensions. It will disappear. But if I have frustration, for example, if I have antiferromagnetism on a triangular lattice, I can also have a frustration. And this in order to map frustration, it means I have exchange interaction, which I cannot describe. It's not sufficient to describe them by a quadratic form here. Maybe I need an additional term here, which is the 4th order term. And then if I have a competition between the 2nd order term and the 4th order term, I can also stabilize the topological objects. And the difference and there will be also topological objects of finite size, and there will be also skyrmions. But these skyrmions, so to say, are stabilized by higher order powers here, and they are not homochiral. So you can have right rotating ones and left rotating ones on the same sample. But you can have them.
All right, thank you. The next question is by Hardip Mandar. Do you always need to induce DMI and intern skyrmions by heavy elements? As you have seen in AFM ferromagnetic exchange biostructures, like iridium, manganese, cobalt, iron, boron, skyrmions have been observed without any heavy layer. Is it due to symmetry breaking at the interface?
Yeah, probably there's also iridium in this sample. Iridium is a heavy metal, I would say. But in principle, it is sufficient. It is. Basically, you need if you want to have DMI, you need some symmetry breaking. There is no way out. And now the question is whether you want to do symmetry breaking. You want to have a strong symmetry breaking, a weak symmetry breaking, a strong DMI, a weak DMI, and then you have to manage this. So in principle, probably you can have also a DMI without heavy metals, but then your DMI is weak. And it means basically maybe your Skyrmion becomes so small that it's not stable.
Yes. Thank you. There is a question by Professor Sampath Kumaran. Please unmute and ask.
Yeah. So I just want to ask you, I missed a part of your talk. You made a statement that independent Skyrmions are metastable. What exactly you mean metastable in the context of magnetic Skyrmions? Do they form, do they exist, or they don't exist?
Yeah, I'm also metastable. I'm existing because my final state is the death. So I think they can, a domain wall is also metastable, but exists maybe for years. Every bit, maybe many bits in the computer are metastable, but they still exist. I think so. Metastability, for example, a diamond, which you may buy for yourself or for your wife, is also metastable, but it stays maybe for thousands of years, maybe for millions of years.
Okay. Fine.
So in this sense, for example, at the end, a diamond should decay into graphene.
Okay.
In this sense, it can be. It is metastable, but it depends. It can be metastable on the scale of picoseconds, where it basically decays into a spin wave, but it can be also stable for 100 years. This depends on the very small parameters has to change to change this barrier and also this prefactor.
Okay. Now that is a continuation of this. Before you really form a Skyrmion lattice, can you form independent Skyrmions, uncorrelated, like you talk about Kondo impurity to Kondo lattice transformation in Kondo lattices? In the paramagnetic, can you have independent Skyrmions in the paramagnetic state before you get into the ferromagnetic state and then Skyrmion?
This is a very good question. So what can happen is, so in principle, of course, if you lose the magnetization, so there are certainly cases where with the above Curie temperature, the magnetization is lost.
Correct.
And then maybe you cannot. You have different situations. You can have a situation where you have maybe you remain some near order, and the long range order is left. But in this particular case, I could imagine that, so to say, some correlation length, some correlations, Skyrmion correlation is still there. I can imagine this.
Okay, because there are certain materials. In fact, recently I wrote an article where I speculated some articles. There are some interesting transport anomalies and magnetic anomalies of just above the Neal order or Fermi order. So we have sort of speculated there's a possibility of formation of uncorrelated magnetic Skyrmions. That's why I asked you the question.
So if you look at the, for example, if you look at the correlation length or the correlation length, for example, of the spin correlation length. And you can also look at the same thing about the spin chirality correlation length, which is so to say the expectation value of Si cross Sj versus Si dot Sj. Then you see that in some cases, for some materials, this chiral correlation length is much larger, or it exists or remains at much higher temperature than, for example, the conventional one. So in this respect, I could imagine that, so to say, this chiral correlation stays longer.
Thank you.
Thank you, Professor Sampath Kumaran, for joining. So I think we have several more questions. Probably I will take one question, Sansivani. If I get multiple Skyrmions in the output, then how do I find out the topological charge of single particular Skyrmion?
So typically, you have a certain density of Skyrmions in your experiment, and somehow you probably can measure the anomalous Hall effect. You can measure the deviation of the anomalous Hall effect, and probably you can normalize that. So that's what I think. So maybe you can normalize the number of Skyrmions by measuring the Hall effect, and from that you can somehow relate to topological charge of one Skyrmion.
Okay, there is one interesting question from a student I have to take, Ankit Lab. Is Skyrmions at zero magnetic field not possible? Is it constrained by theory?
I think also Stremians at the zero field are possible.
I think they are already observed experimentally.
No, sometimes it depends on the situation. Sometimes you need you have to apply a certain magnetic field. Sometimes you don't need to apply a magnetic field.
Yes. So I think it is not really constrained by theory.
No, no.
Yes. It is, I think, all about the the combination of the material parameters. So sometimes it's possible without field, but most of the time people have to apply some Zeeman energy to basically get it.
Yeah, sometimes you have to get into the right regime where you just discriminate form.
Yes. Professor Sampath Kumaran, you have a last question?
Yes. I have another short question. Sorry, I forgot. Can we have Skyrmion glass? Like you talk about spin glass.
I think this you can have.
You can have, I see. Is there any indication in the experimental data from any material?
Oh, I do not know. No, sorry, I'm not the expert for that.
Okay.
Yeah.
So in principle possible. Okay, fine. Thank you.
Okay, thank you. Thank you so much to all. Stefan, could you please stop sharing? I like to share my screen and we like to present you a small digital plaque. Okay. So do you see my screen?
Yeah. Yes.
Okay. Yeah, so it's a small token of appreciation from our team. So I just read it for you. W2A seminar webinar series on Spinorbitronics, Mysore, Bhubaneswar, India, takes pleasure in presenting this plaque to Professor Stefan Blügel from Forschungszentrum Multilayers in Germany in recognition and appreciation for being a valuable speaker to give a lecture on chiral magnetic Skyrmions for Skyrmionics. So thank you so much, Stefan, for your very kind acceptance of our invitation and spending your very valuable time to give a lecture. I think it was a very nice discussion. Everybody enjoyed. I just want to announce that next week, the lecture will be given by Professor Henry Koldak from Lawrence Berkeley National Laboratory. So see you next week. I wish you all good health. And Stefan, again, thank you so much. Have a nice day. Bye-bye.
It was a true pleasure. It was a true pleasure to interact with you. Yes.
Thank you so much.
And to share my results with you.
Yes, thank you so much.
If there's further question, please send me an email.
Yes, sure. I will do that. Thank you. Bye-bye.
Bye-bye. Bye-bye, Ashish.
Bye.
It was great seeing you.
Yeah, good to see you.
Yes, bye. Puspendra, you can now stop recording and also close. Thank you, Puspendra.